For the past 3 months, I've been working on a tool for providing automated formal verification for Daml code. So what this means is that we want the computer to automatically say, given a choice and given a specific field in a template, then a tool should automatically prove that no matter the input to this choice, it will always preserve the total amount of this field in the world. So for example, a choice might move funds between accounts, but it should never destroy or create new funds. So the tool is still a prototype. So I can very much demo the prototype, but the idea would be to integrate this into an IDE later on. But for now, it's just a command line interface to show you what the tool can do. So I'm going to try to share my screen. Okay, can you see that?
Yeah, we can. Thank you.
Okay, cool. So for the purpose of this demo, I created a small example, a template account, which is simply it stores an amount and it has an owner. And then I have this simple choice here, which just transfers funds between 2 accounts. So it takes an amount to transfer, it takes a receiver. If the donor doesn't have enough funds to transfer, it just doesn't do anything. And otherwise, it fetches the receiver and it creates the remaining donor and a new receiver. So obviously, we want this choice to preserve the total amount of funds. So let me just build this star. Okay. So we can now pass this into the verification tool. So we pass in the DAR. We pass in the choice, which in this case is account transfer, and the field we wanted to preserve the total amount. Okay, so immediately the tool tells us that something failed. The choice doesn't actually always preserve the amount, and it provides us with a counterexample here. So it's still a prototype. The output is not the easiest to read, but it does provide us with some information. So basically, it describes the main flow. I should make this a bit bigger. It describes the main flow of the choice. So when executing the choice, it makes a number of create and archive updates, which are described here. So if this condition holds, so if we have sufficient funds, then we create a new account with the current amount minus the transfer amount, and with the receiver amount plus the transfer amount, and we archive the receiver. So indeed, clearly something is wrong here, and we forgot to archive the current the self. So if we add this line, archive self, and we try this again. Well, now the choice actually always preserves the amount, because now we also archive the current amount. So before I mentioned that this choice should always preserve the amount no matter the input of the choice, but the tool actually does take some more information into account. So for example, this ensure is actually, the tool is actually aware of this. So if, for example, we would add something more here, if we would say, if the transfer amount is smaller than the amount, then we do something else. We fetch the receiver. And if the receiver amount is smaller than 0, and we do something silly like, let's say we create new receiver with amount of 10, and we return receiver, return self and new receiver. So you might expect this to break, as clearly this doesn't preserve the amount, but the tool is smart enough to figure out that because the amount can never be negative, we know that the receiver is an account, so this branch can never happen. And I can show you, just rebuild. And indeed, the choice still preserves the amount. Let me just remove this again. Okay, so all of this already worked in the last demo we gave. So what is new since then? Well, now we extended the tool with support for recursion. So for example, I wrote this second choice, which basically it donates from one account to another until the account has at least as many funds as the donor. And it does this by checking the condition. If the receiver already has enough funds, then we don't do anything. If not, we use our transfer choice, which we defined before, to transfer one into the receiver, and then we call the thing again. So it's a recursive choice that keeps calling itself until the receiver has enough funds. So let me build the example again. There we go. And call the tool with this new choice. Okay. So this gets a bit more complicated. How does this work? Well, we can't make any assumptions on the input. So based on the input, this might make a number of recursive cycles. But we don't know how many cycles it makes. So basically, what we do is the tool extracts every possible recursion cycle. It extracts it from the code, and then it also describes the main flow. So the main flow is what happens if you run through the choice once, and then the recursion cycle is the cycle that gets repeated every time you call choice. So in order to ensure that the amount is always preserved, we require that both the recursion cycle at every iteration step preserves the amount, and that the main flow preserves the amount as well. So this is slightly overly restrictive. So there might certainly be some examples where this isn't the case, but which still preserve the amount. But while designing this tool, we really had the goal in mind of making sure that when the tool says that the amount is preserved, that it is actually the case. So a false positive is much worse than a false negative. So we made the tool a bit overly restrictive. This can certainly be improved later on. So, okay. So the tool can figure out recursion cycles now, but we can actually go one more step further. Namely, we can go into mutual recursion. So I wrote this final choice here. It is a bit overly complicated. It's designed to be to show off the tool. But basically what it does is it takes an account, and it takes an integer, and then it splits the account into a number of equal chunks. So if you have an account containing 10 amount, and we split it into 5 chunks, then we should end up with 5 chunks of 2. I know that this choice could easily have been written to be much simpler, but let's just go for it. So basically what it does is it checks whether it needs to create an additional chunk. If so, then it calls the second choice. And all this does, it's just creating an additional empty chunk with amount 0. It then calls the third choice, which computes how much to transfer into this new chunk, and then use the choice we defined all the way to start to make it transfer into this new chunk. And then it calls the first choice again with one less chunk. So this makes a number of cycles through these 3 choices. And the tool is now able to isolate these mutual recursion cycles. So I can show you this. If we call the tool account divide, what do I call it? Oh, breakup. Sorry. Okay. So what happens here? The tool figures out that there is a mutual recursion cycle between these 3 choices. It then isolates the cycle itself. So every update that happens within these 3 choices, which are described here. And then in this case, the main flow would be empty. So the choices only have this mutual recursion cycle and nothing else. And then again, it needs to ensure that both the main flow, which in this case is trivial, and this mutual recursion cycle always preserves the field, which in this case it does. So in this case, it's still relatively easy because the mutual recursion cycle encapsulates the entire choices. But for example,
sorry, just a quick question. Can you
yeah,
say a few more words about the main flow, it being empty? What does that signify exactly?
Yes. So in this case, this is only a simplification. So why is this empty? It basically means that if we call this account breakup, it runs through the entire code again and again, but there is nothing outside of the cycle. So let me show you what happens if this wasn't the case. So the cycle goes through the if here and exercises create chunk. So it goes through all of this and then back to breakup. However, if you make an additional branch here, saying, for example, let's do create this with. So now this part, this else branch, is no longer a member of this mutual recursion cycle. It doesn't get reached at every iteration, only at the very end. And the tool takes this into account. So if we rebuild, okay. Okay. The cycle itself remains completely identical, and it still preserves the amount. But the main flow suddenly got a whole lot more complicated. So outside of the mutual recursion cycle, there is now this additional else branch. So this is not part of the cycle, but it does happen a single time when you execute a choice. At the very end, this gets executed, but not at every iteration. So now this main flow is no longer empty. So now it needs to take one cycle plus this end condition into account. So all of this is one cycle. And then here you see at the very end, if the number of chunks is no longer larger than 1, then we create 10. Meaning that while the cycle preserves the field, the main flow no longer does, because at the very end it executes this additional create statement. Does that make sense?
Absolutely, thanks a lot.
Okay, so that's actually basically what I wanted to show. The tool is still a prototype, but it does show quite a lot of potential. It can already verify quite a set of programs, and it would be really interesting to see where it goes after this. It would be great to have it integrated within an IDE so it can be used more user-friendly without having to go to this command line interface.